everyone. Welcome back to Learning at 11th Hour. In this video, we are going to look at capacitors and capacitance. To explain how capacitors work, I'm going to take the help of PHET interactive simulations. So let's just directly go to the simulation. So a capacitor is basically an electronic device which can store energy. A capacitor can consist of two metal plates which is separated by a non-conducting material or a dielectric. So let's look at this. In this scenario, we have two parallel plates. So a capacitor could consist of two metal plates, right? And they are separated by the dielectric material, which in this case is air. We could have any other dielectric material. In that case, the permittivity of that material will change, which of course will cause a change in the capacitor's value. Now, here we can see two parameters. One is called the separation, which is the separation between the two plates, the upper and the lower plate. The other is the area of the two plates. So let's see what happens to the value of this capacitance if I increase the separation. So as the separation increases, the capacitance value decreases. As the separation is decreased, the value of capacitance increases. Secondly, if I increase the area of the plate, proportionately, the capacitance value also increases. Whereas if I decrease it, the capacitance value decreases. So from this, we can infer two things. The first thing is that the value of capacitance is inversely proportional to the separation between the two plates. Let me call it as D. And the value of capacitance is proportional to the area of the two plates. Let me call that as A. It is also going to depend directly upon a parameter called epsilon, which is nothing but the permittivity of the dielectric. So, in that case, we can put together the three terms and we can say that the capacitor has a value of C, capacitance, given by epsilon A by D. Here, epsilon R represents the relative permittivity. It is measured relative to the permittivity of vacuum, which is denoted as epsilon naught. So, therefore, we take the epsilon naught as the reference and measure the permittivity of any other material as epsilon R, which is by the R in the expression. So, this is the expression of a capacitance. The unit for capacitance is farads. Now, if I apply some voltage across the two plates, then what happens? So, these are the two plates connected across a battery. When I increase the voltage, there is accumulation of charges on the two plates. So, why does this happen? So, the battery causes, so this is the positive terminal of the battery and this is the negative terminal. The positive terminal tends to attract the uh, negative charges from the plate, and the negative terminal attracts the positive charges from the plate. So, therefore, what is left behind in the plates is the positive charges in the upper plate and the negative charges in the lower plate. So, because of this, there arises an electric field, okay, moving from the upper plate towards the lower plate, from the positive to the negative direction. So, there is an electric field which exists between the two plates. Now, if I tend to change the direction of the applied voltage, then the direction of the applied electric field also changes. The amount of energy which is stored in the capacitor will also vary as I vary the voltage applied to the two plates. Now, does this really act like a storage device? We can find that out by connecting the two plates or this capacitor to a light bulb. But I'm going to disconnect it from this source first. After I charge it, I'll disconnect it and then connect it to the light bulb and see if the light bulb really glows. So now I have the capacitor connected to the battery and a lamp, but it has not yet been connected to the circuit. So let me now charge the parallel plates. Right now it is devoid of charges. So if I increase the voltage to 1.5 volts, let me measure the voltage on the two plates. So across the two plates, the voltage is actually 1.5 volts. Let me put it back. Now, if I disconnect the capacitor and connect it to the lamp glows. But if you see, it is observed that the charge on the plate reduces over a period of time, and so does the brightness. And this continues to happen till the capacitor's charges are completely discharged through the lamp. So, this phenomenon is called discharging of the capacitor. So, I can charge it and then I can connect it to a load like a lamp, wherein it will act like a source, but it will only act like a source till it has charges in it. Once the charges are discharged, it is not going to act like a source because it will have no charge carriers in it. The energy in the capacitor, how much energy does it store? So that can be computed. So let's say the charge Q that the capacitor's plates can hold is given as C into V, where V is the voltage applied, C is the capacitance of the capacitor. We know that the rate of change of charge over a period of time is current. So dq by dt is nothing but I. So I can differentiate on this side also. So what I get is C dv by dt. So we see that the current I is given as C dv by dt. Now, if I want to find out power is given as V into I. So I can say it is given as C into I is replaced as dv by dt, C dv by dt, and the V remains. So this is written as C dv square by dt, or half CV square. So this is the power. Now, if I can find the energy that the capacitor can store, so I'll have to do that over a period of time. So integration of P dt over T1 to T2. So I can say that this will be given as half into C V2 square minus V1 square, which is nothing but half C. I can call the difference as some capital V, the whole square. So this is the energy stored in a capacitor. So I came across this wonderful summary in Shom series of all the circuit elements and the relations between voltage, current, and power. So as far as the resistance is concerned, the units of resistance is given as ohms and it follows the Ohm's law. So we get the expression the voltage is equal to the product of resistance into current. V is equal to IR. So therefore, obviously from this we can rearrange and find out that I is equal to V by R. The power relation here can be written as V into I, and I again can be replaced with V by R. So I can obtain the relationship as V square by R, or I can replace V with IR and obtain the relation I square R. And the next element is inductance. The units is henries, and the voltage is given as L di by dt. So that is the rate of change of current into the inductance, and the value of current therefore can be rearranged, and when you get the dt on this side we get L di, and in order to find the value of I we need to integrate. So what we will get here is 1 by L, this being a constant, it can come to this side of the equation, integration V dt plus the constant of integration is equal to I. So this is the relation over here, and power again can be given as L into I di by dt. Next is capacitance. The units is farads, and the voltage can be given as V is equal to 1 by C integral I dt plus K, where K is the constant of integration. So this arrives from rearranging and integration of the current relation, that is I is given as C dV by dt. The power is C into V dV by dt. So that's the summary of all the circuit elements in use, the voltage, current, and power relations. That's all with today's video. I hope the concept of capacitance is clear to you all. Please do subscribe to this channel and keep watching more such videos on circuit theory. Thank you.